Yeah, so I was talking about something from the last video. This part I've done it in that video, but it was cut off somehow by my phone. So let me go and quickly talk about it. I said that when you have the numerator to be a derivative of the denominator, you can easily get the integral of the function, this quotient, by simply taking the ln of the denominator. Why is that? I mean, generally you can write it this way, that if you have some function q prime of x, that means if you have q of x at the denominator and you have its derivative q prime of x at the numerator and you want to integrate this with respect to x, it is simply ln q of x of course plus your constants, whatever constants of integration that would be. All right, so then so here we're saying that that is quite straightforward to get, because this here is what you get when you differentiate this using your product rule. I mean, a function of a function, you're going to have these as um, differentiating with respect to the core. If you want to differentiate ln of q of x, that would be 1 over q of x, then multiply by derivative of q of x to give you q prime of x. So it's quite straightforward to understand that way why it's integral. I mean, this is just q prime of x over q of x, so its integral definitely will give us this ln q of x back, and that will be that. But there's an error here. There's an error where we started. The error was this. Earlier I wrote here this derivative of y squared minus y with respect to y. I wrote only 2y before. It's meant to be 2y minus 1. Okay, so here we're meant to have 2y minus 1. Of course, this is still I mean, for this case, this is still not a function that depends on x, so we cannot use that approach. But here, this is meant to be 2y minus 1. So if this is 2y minus 1, at the end of the day, we're going to get our, so let me just correct that here. You can see that we're going to have this our h of y to actually be not this expression that we have here before. So this is not correct. So I'm going to just cross that out. Of course, we're still going to use this formula, but h of y is actually going to be 2y. From here you have derivative of this to be 2y minus 1, derivative of this to be 1. So this is going to be 2y minus 1 minus 1. That will be 2y minus 2 divided by this, which is y squared minus y. So somehow this can be factorized to give 2 into y minus 1 all over y into y minus 1, and then at the end of the day we can cross that out. This is going to give us 2 over y. Okay, so that's what we're going to use. This is not this complex. Of course, if you add any situation like this, of course this will be its integral. You just take ln of y squared minus y, but that's not the situation here. So let me continue on a clean sheet so that you'll see what I'm talking about. So that means that our, sorry, this is off work already. So let me see. That means we're continuing here now with this. That means our value that we need here is actually going to be, I mean, what we need here, the integrating factor I of x comma y is going to be e raised to power minus integral of our h of y is 2 over y, so that is 2 over y dy. That will be equal to e raised to power. So this is wrong. I had actually done this in the video. The part that I said was cut off, so that's why I had used this result directly where there was an error here. So that's what brought about all of this. Okay, but then if that was the situation, I noticed the error on getting to this point, that this did not become exact at the end of by after multiplying by the result. So that was when I went back to check and find out that I had made a mistake here. So and now, so let's proceed with this. This is going to give us minus 2 right there, integral of 1 over y dy. So that's quite straightforward. Now that's going to be e raised to power minus 2 integral of 1 over y dy, that is ln y. Of course, as I said before, we are going to ignore the constant of integration always when we get to this point. So this is going to be e raised to power ln y raised to power minus 2. So it's quite easy to get that. So this is going to give us this e, we cancel this ln, so that's going to give us y raised to power minus 2. Okay, y raised to power minus 2 is going to be 1 over y squared. So our integrating factor is 1 over y squared. That means we are suggesting that when we multiply this equation by 1 over y squared, it will become exact. So let's try that now. So we have here y squared minus y dx plus x dy equal to 0. So when we now have to multiply it by this integrating factor and see what that gives us. Of course, we know this is not exact. Let's see if the resulting equation will be exact. So multiplying this, we're going to have this to be 1 over y squared into y squared minus y dx plus x over y squared dy equal to 0. So we can simplify this further. Y squared over y squared is 1 minus y over y squared, that is 1 over y dx plus x over y squared dy is equal to 0. So is this exact? Let's check. This is going to be our new m of x comma y. This is going to be our new n of x comma y. So if I differentiate this partially with respect to y, what is it going to give me? Now our del m of x comma y del y will be equal to the integral of this, derivative of this partially with respect to y. This will be 0, then this will be minus of whatever we get now. Bottom the top will be 0, that's y multiplied by 0 minus top the bottom. The top is 1 and the bottom is derivative of the bottom is 1. Okay, all over bottom square, that is y square. So this is going to be minus of minus 1, that is 1 over y squared. Okay, and then if I take n of x comma y and I differentiate it partially with respect to x, I'm going to have del n of x comma y del x to be equal to, differentiating this, that is just the coefficient there, which is 1 over y squared. So obviously now this equation has become exact, so we can now solve it using our usual method of exact differential equations. So and don't forget, I told you there's no need to go through that long process in an OBJ question. So just do that here, and if you can also still go through the long process, you'll get the same results if it were a theory question. So that was why I needed to go through that long process starting out. So but now we're good to go, so we can just you can remember what we said. You will integrate this with respect to x. You integrate with respect to x. Don't forget, it's different from when we are checking. When we are checking, we are differentiating with respect to y, the coefficient of dx, and differentiating with respect to x, the coefficient of dy. But if you want to solve, you are integrating. So you can imagine that, you can even imagine that you are doing something like integral, then you are doing this with respect to x, then this with respect to y. Then you want to write out the results. Then whatever is common to both of them will appear only once, and then you put your constant of integration and equate it to 0. That will be your solution. So integral of this with respect to x is going to be x minus x over y. Okay, hope you got that. These are constants, so they just carry x like that. And then the integral of this, okay, with respect to y, so that will be integral of x over y squared with respect to y. So that will be integral of, that will be x multiplied by the integral of minus 2, okay, dy. So that will be this part. So we're considering this part alone, and this will be equal to x y minus 2 plus 1 over minus 2 plus 1. So at the end of the day, we're going to have this to be equal to x, y minus 2 plus 1, that's minus 1 over minus 1. So this is going to be minus x over y. So you can see minus x over y is here, minus x over y is here. So whatever is common to both of them we appear only once, then the others will be included also. So at the end of the day, we're going to have our result to be x minus x over y, then that's all we have, then plus c is equal to 0. That is the solution to differential equation. So as before, you can check to convince yourself that this is correct. Okay, you can see that. So this is x minus x over y. So whatever appears to both of them, whatever is common to both of them appears only once. Then we put in every other term there. So that's x. There's no other term here. So this is just x plus this, then plus c equals to 0. So that's that about that. So I think we're done with these differential equations 1. So please ensure you work on the other examples just to see, just to gain confidence with this method. And that's that about that. So the next is to actually consider the last material on differential equations. So let's quickly consider the last material on differential equations. That's differential equations 2, where we consider different kinds of other kinds of differential equations you may come across. Okay, so that's I know with Professor Akinola's part of the material. I've sent these questions to you already, so I'm going to take them one after the other. So the first part has to do with what we call linear differential equations, first order linear. Of course, we've talked about linear differential equations before, so we should still remember if we say that a differential equation is linear. So so for our case here, we'll say that our linear differential equation is generally going to be of the form, it's going to be of this form: the y dx plus p of x multiplied by y is equal to q of x. Okay, you can remember our definition of linear differential equation. Of course, this is linear. I have the y dx to not be squared. It is not square. Y is also not square, and there's no product of y and the y dx. So this is strictly a function that depends only on x. This is a function that depends only on x also. So this is linear, but it is not homogeneous based on our definition of the homogeneity of linear equations. This will be homogeneous if q of x is 0. Okay, so but that's not the situation we are considering here. So if we have these linear equations, how do we go about actually solving this? We can also use the same idea we just used now for the part we just concluded, which is that we're going to check if it is exact. Then if it is not exact, then we're going to get an integrating factor for it. Okay, so basically, okay, maybe I should show you or just tell you directly. Whenever you have equation of this form, okay, you can, for instance, you can break it down into, or you can write it in such a way that it looks like the what do you call it now? It looks like the equations you are familiar with, the equation, the inexact equations you are already familiar with. That means you write it in terms of the y and the x. For instance, I can say that this is the y dx is equal to q of x, or let me put this together. Let's do it this way first. It's equal to q of x minus p of x multiplied by y, and then I can multiply it through. This is going to give me the y is equal to q of x minus p of x y, then everything here multiplied by the x. So this is our coefficient of the x, this is our coefficient of the y, which is 1. So if I put them together just to look like something obtained from a differential, this will be this minus, or say plus, and I multiply this by minus. When I move it here, it will now be p of x y minus q of x, then the x is equal to 0. So it is obvious that this is not exact. Why? Okay, let me rearrange this to avoid confusion. Let's say this is p of x y minus q of x, okay, everything dx plus 1 dy. Putting 1 there to avoid confusion also, equal to 0. When I differentiate this partially, if I want to check if it is exact now, I'll differentiate this partially with respect to y, and differentiate this also partially with respect to, when I differentiate this partially with respect to x, it's going to give me 0. When I differentiate this partially with respect to y, definitely it is going to give me p. So in this case now, let's write it out. Our m of x comma y is equal to p of x y minus q of x, and then our n of x comma y is equal to 1. So it is obvious that when we differentiate this, del m of x comma y, okay, del y is going to be equal to p of x. That's just the coefficient of y here. Y is not here, so that one is gone. And then we're going to have del n of x comma y del x, okay, del x in this case, to be equal to 0. So it's obvious they are not the same, okay, except p of x is 0. So if p of x was 0, then there will be no, if p of x was 0, there will be no need to even consider this case, because then it will just be a separable differential equation which you can solve using that direct integration that we've done before. Okay, so in this case it will always not be 0. Okay, so this is obviously not exact. And then we can now check our conditions for getting integrating factor. So we see if we can actually get an integrating factor for this problem. And so, like we said before, we'll consider this condition first. We'll try to get difference between this, then divide that difference by n, and see if it's a function that's going to be dependent on x alone. And it's obvious here that that is true, but let's work it out. We're going to have 1 over n, okay, make sure you're seeing that on the screen, 1 over n into del m del y minus del n del x is going to be equal to 1 over, so what is our n in this case? You have seen that already. Our n is 1, so that's 1 over 1, this n here, 1 into del m del y. Del m del y is p of x, that's a function that depends only on x, then minus del n del x, which is 0. Okay, so when I put all of this here, this is obviously going to give me p of x. So it is obvious that this is just strictly a function that depends on x, as we would like to have it here. So from here we know that we can always solve this problem, this kind of linear first order linear differential equations, by getting an integrating factor. So that means in this case I can get my integrating factor I of x comma y to be equal to e raised to power integral of p of x, because our p of x is the g of x we need here now, the x. And indeed that is the general way to solve equations of this type. You will just get this coefficient, this x, for this function that depends on x, that is coefficient of y. When you've written the equation in this form, or you are given the equation in this form, you may be given directly in this form, or you have to rewrite it in this form. It's fine. If you are not given in this form anyways, you can check directly that it is not exact, and then find out if you can get an integrating factor for it as before. But if you are given in this form, it just makes your work faster. You already know how to get the integrating factor. You are just going to use this p of x directly to get your integrating factor. So that's the approach here. And when you get the integrating factor as before, we multiply the equation by the integrating factor, we will get an exact differential equation, which we will then solve using our familiar method of solving exact differential equations. So life can be as easy as that when it comes to this. All right, so let us consider some of the problems now that we have here. So I'm going to solve one of them with you here, then you solve the other. So look at it. It says sum for y of x if the y dx plus 2xy is equal to 4x. You can see it's already in that form. It's already in this form. Now look at the general form that we talked about. This equation is in that general form. This is the y dx, this is something y, so this is something y. So that means p of x is now 2x for this situation, and q of x is 4x. Okay, and now look at the second one too. The same thing. You have y prime. Don't forget y prime in this case, your independent variable is x, so that means that y prime means the y dx. So something similar, the y dx, then y cot x. That means p of x is cot x, then multiplying y, and then your q of x in this case is 1. So we are good to go. So you can use the same method for both. So I'm going to solve the first one, which is expected to be the simple one. As a good teacher, you should solve the simple one so that you will try your hands on the top one. So but then the approach remains the same. So for this problem now, we have been told that the y dx is equal to the y dx plus 2xy is equal to 4x. So in this case, I can identify directly what I will need to get my integrating factor. P of x is equal to 2x. So then my integrating factor, this new lecturer usually denotes this as mu of x, but it just means basically the same thing, okay, as what we did before. Alright, now this other lecturer is just making use of the concepts you have learned before to actually apply it in another way. So it's not, this portion is not really anything new or different. Okay, I just want to be formal and in proper alignment with his notations. That's why I'm using mu of x. We know that this is just going to be a function that depends only on x, so we can just say mu of x instead of writing I of x comma y. So this is going to be e raised to power integral of 2x, okay, dx. So that is going to be equal to e raised to power integral of 2x dx, that is x squared. So life is as easy as that, as easy as it can get, right? So we are now going to multiply the equation all through by e raised to power x squared. So that means at the end of the day, I'm going to have e raised to power x squared, okay, dy in the x plus this e raised to power x squared into 2xy is equal to e raised to power x squared multiplied by 4x. So you will notice here that you can get just observe something. Of course, you can do it the way we've always done it, where we write it in terms of the y and the x. But the reason why we're doing this actually is we're actually treating this differently is because this looks way simpler when we approach it this way without having to write it in terms of the y and the x. So there's something you should observe here, okay, it is the fact that this expression here can be written as the x as derivative with respect to x of y e raised to power x squared. Okay, why is this so? Now in all cases this will always be the situation. I can pick y, which I have here, then pick e raised to power x squared, which is my integrating factor. Is this correct? If I want to differentiate this, for instance, how will I do it? This is a product of two functions. So firstly, I will differentiate this while keeping this as a constant. So if I keep this as constant, that will be e raised to power x squared. Then differentiate y, that will be dy dx, plus keep y as a constant, then differentiate this. So when I differentiate e raised to power x squared, that will be e raised to power x squared multiplied by 2x, and then I will have y as constant. So that's how it will come about that 2x derivative of e raised to power x squared is e raised to power x squared multiplied by 2x, then I will have y as the constant. So we just observe that what we have here is the same as derivative of y multiplying the integrating factor with respect to x. Then we say this is equal to e raised to power x squared multiplied by 4x. Now look at this. So now this is now quite easy to do because the variables have been separated for us automatically. So this is just having the y e raised to power x squared to be equal to e raised to power x squared multiplied by 4x dx. And now the integration is also very easy for us to do here. Integral of this is just going to be y e raised to power x squared. Just like integral of the x is simply equal to x, okay, plus c, of course. Integral of the whatever is just equal to whatever. All right, and this is going to be equal to, now to get the integral of this, you don't really need to go that far. It's something you can also deduce from what we have done here already. We know that the derivative of e raised to power x squared is actually 2x e raised to power x squared. So if you have 4x e raised to power x squared, so you can just write this as 2 multiplied by the integral of e raised to power x squared multiplied by 2x dx. So it's obvious that the integral of this is simply equal to e raised to power x squared. So this is just going to give us y e raised to power x squared is equal to 2 e raised to power x squared, then plus some constants of integration c. So I hope you got that. 2e raised to power x squared plus some constants of integration c. So, and then that is that about that. So to make y the subject of the formula here, we can clear off our e raised to power x squared. This e raised to power x squared is raised to power x squared, not ex squared. So we can clear off e raised to power x squared. That's going to give us y is equal to 2 in this case. This will have cancelled. E raised to power x squared will have cancelled it, then we will have plus c. That's the constant of integration we have here, divided by, that will be c divided by e raised to power x squared. That's the same thing as c e raised to power minus x squared. Okay, and then that will be our results. So that is going to be our answer at the end of the day. So that's the solution to that differential equation. So it's always that easy to do and straightforward. So that integration here is quite easy. If you didn't notice that it's that easy, you could also have used product rule. That's integral of u dv is equal to uv minus integral of v du. That's a long journey, but for that, it was a good punishment for not being able to notice here that is actually equal to this, and that's okay for a punishment. All right, so that is that about that. So you can attempt the second part of this, okay, and see how that works. So let's move to the next section. It's about non-linear equations. So you can have equations that are non-linear, and then we want to reduce it to a linear equation. So don't forget that what we just solved now, well, this is the general form of a linear first order differential equation. Okay, so we may have a non-linear equation, and then we are able to reduce it to a linear equation in some cases. So let's consider one of those cases now. So one of them is what we call the Bernoulli equation. So we call it the Bernoulli. So this is Bernoulli's differential equation. Okay, Bernoulli equation. There is one Bernoulli equation under fluid mechanics. I think you should have done that in physics. You'll do it again in 300 level. So we will be offering them in 303 and some other courses. So the Bernoulli equation we're talking about here is differential equation. So Bernoulli actually came up with